Welcome to the deep dive. Today, we're plunging into something pretty startling, actually. It's this idea of profound simplicity, hiding underneath the world's most complex, most chaotic seeming systems. We've gone through a whole stack of sources on chaos and complexity science, and honestly, the main takeaway feels almost too simple.
It really does. Our mission here is to give you the shortcut, the inside track on understanding this huge puzzle in science.
Yeah.
How do things that look completely unpredictable, weather, stock markets, life itself, how does all that emerge from just a few basic physical laws?
It feels like we're searching for the ultimate cheat codes for the universe.
Kind of, yeah.
Yeah.
Finding those few rules that govern all the infinite mess we see around us.
And here's the real hook. Something physicist Jim Lovelock pointed out. His work is fascinating. We'll get into it. He basically said the entire field, all of chaos theory, all of complexity really boils down to just two core ideas.
That's it. That's the deep simplicity right there. Any complex system you look at, it's showing you these two things in action. First, how incredibly sensitive it is to where it started. Tiny changes have huge effects.
Okay. Sensitivity.
And second, feedback mechanisms. Loops within the system that regulate or amplify things.
Wait, hang on. Only two. That feels almost offensively simple. We're talking weather prediction versus, say, galactic evolution. And that massive difference is just starting points and feedback.
That's what the science suggests, yeah.
Yeah.
It's a bit mind-bending. And to really get why this is such a big deal, we need to rewind a bit, back to where classical science kind of hit a wall, back to Newton.
Okay, right. Let's set the stage with classical physics, the golden age.
So 17th century, Isaac Newton, building on Galileo's work, he lays down these universal laws, gravity, motion laws, beautifully simple, incredibly powerful. You've got two things orbiting, like Earth and the Sun. Newton's laws let you calculate their paths perfectly forever.
Total predictability, which led to that deterministic view, right? Laplace.
Exactly. Laplace's demon. The idea that if you knew the position and momentum of every single particle right now,
you could calculate the entire past in Fisher, like a giant clockwork mechanism.
Clockwork universe, yeah. No room for surprise, maybe no room for free will even, it's all predetermined. But even with that success, physics ran into a snag, a mathematical one.
The Newtonian wall. And this wasn't quantum weirdness yet, this was basic gravity stuff.
Purely classical.
Yeah.
It's the n-body problem, specifically the three-body problem.
Sun, Earth, and Moon.
Perfect example. We know the laws, Newton's gravity applies to all three.
Yeah.
You can write the equations down, but you can't solve them analytically. Not with pen and paper anyway.
Yeah.
They're non-integrable.
So the rules are perfectly known, but the outcome is mathematically unsolvable in a neat formula. You need to simulate it step by step.
You got it. That's exactly what non-integrable means.
Yeah.
The system is still perfectly deterministic. It follows the laws precisely. But because there's no neat solution, its behavior becomes practically unpredictable, chaotic, really quickly.
Wow. So that was a first big crack in Laplace's perfect clockwork. Determinism doesn't actually guarantee predictability.
Precisely. And that just adds to the weirdness. Like, classical laws seem time reversible. Run a billiard ball collision to backwards, it still makes sense. But reality obviously has an arrow of time, right? Things break down, entropy increases. The second law, always forward.
Okay, so classical physics had these hints of trouble. But the real chaos revolution needed something else.
It needed computers.
Yeah.
Fast ones. Jump forward to the 1960s. Suddenly scientists could actually simulate these messy real-world systems. Weather was a big one. And then these ideas started linking out, through books like Order Out of Chaos by Prigogine and Stengers, or James Gleick's Chaos.
Which brings us to Edward Lorenz, the meteorologist. This feels like a key moment. What happened there?
It was almost a lucky accident, really. Lorenz was running these weather simulations using equations full of feedback loops, standard stuff for weather modeling. One day, he wants to rerun a part of his simulation. To save time, instead of typing in the full 6 decimal place number from the previous run's output, he just typed in 3 decimal places, rounded it off, a tiny change, like 1 part in 1,000 difference in the starting temperature or wind speed.
Just to save a few seconds typing. And he accidentally discovers this fundamental limit on prediction. Okay, so what did the new simulation show?
At first, the graphs looked exactly the same for a little while. But after a few simulated weeks, the two runs diverged wildly, massively. The new weather pattern looked nothing like the original one.
Because the tiny initial error wasn't just added, it was amplified.
Exactly. Amplified exponentially. That's the nature of nonlinear systems. Unlike simple linear ones where small input errors give small output errors. Nonlinear systems have these feedback loops that just blow tiny initial uncertainties way out of proportion over time.
Which gets us back to Lovelock's first pillar, extreme sensitivity to initial conditions.
That's it. This is the practical reality of it.
And this becomes the butterfly effect, Lorenz's famous paper title from '72. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?
Hmm.
It's a perfect metaphor, isn't it? Tiny cause, potentially massive, unpredictable effect somewhere else down the line. Limits weather forecasts, fundamentally.
And it ties right back to that three-body problem. Sun, Earth, Moon again. Their motion is deterministic, follows Newton's laws perfectly. But that sensitivity means even the tiniest uncertainty in measuring their positions now makes predicting their exact positions way out in the future impossible. It's chaos, but it's born directly out of deterministic rules.
Okay, so chaos theory tells us long-term prediction is often impossible. Seems kind of depressing for science. But that wasn't the end of the story, was it? Scientists started finding patterns inside the chaos, order within the unpredictability.
Exactly. That's the next really cool part. When you track these chaotic systems, not just through space, but through their possible states, what we call phase space, they don't just wander randomly. They trace out these incredibly intricate yet structured patterns. Shapes called strange attractors.
Strange attractors. Okay, why strange? And what exactly is phase space? Just a complicated graph.
Good question. Think of phase space as like a map of all the possibilities for the system. Each point on the map is a unique state. Maybe it's a velocity, its temperature, whatever's relevant. The attractor is the path or region in this map that the system tends to follow over time. And it's strange because, well, these paths are infinitely detailed. They never quite repeat the same way twice. And crucially, they have this weird property.
Yeah.
A fractional dimension, a fractal dimension.
Ah, fractals. Benoit Mandelbrot, I love the coastline example. How long is the coast of Britain?
It's a perfect illustration, yeah. Mandelbrot asked that simple question.
Yeah.
And the answer is, it depends on your ruler. Use a big yardstick, you get one length, skipping all the tiny bays. Use a tiny millimeter ruler, tracing every nook and cranny, and the length gets much, much longer.
And if your ruler gets infinitely small, the coastline length becomes infinitely long.
Theoretically, yes, because the pattern of jaggedness repeats at smaller and smaller scales. It's scale invariant. That self-similarity across different scales is the hallmark of a fractal, and it shows there's a deep structure there, even if it looks ragged and random.
And this fractal geometry often shows up alongside something called power laws, right? Which describe how often events of different sizes happen.
That's right. Power laws, sometimes called scale-free distributions or Yi noise, pop up everywhere in complex systems. Earthquakes are a classic example.
Yeah.
The Gutenberg-Richter law describes earthquake frequency versus magnitude. Plot it on a log graph, and you get a straight line. That's a power law signature.
And the implication of that law? It's kind of mind-blowing. It means huge earthquakes aren't caused by some special, super rare mechanism, are they?
No. The law strongly suggests that the biggest, most catastrophic earthquakes are generated by the exact same underlying physics as the tiny tremors we don't even feel. Big ones are just much, much rarer according to that power law relationship.
So we should stop searching for the unique trigger for the big one.
In many systems, yes. The focus shifts. Instead of looking for the external cause of the catastrophe, look at the internal dynamics, the simple rules that generate events of all sizes.
Okay, which brings us to, how do systems naturally get into this state where they follow power laws and look fractal? This self-organized criticality idea, SOC.
Right. This was Purbach's big contribution using the sandpile model. It's brilliant because it's so simple. Imagine just dropping single grains of sand, one by one, onto a flat surface. A pile builds up.
Okay, got it.
Eventually, the slopes of the pile reach a certain steepness, a critical angle.
The edge of chaos we hear about.
That's the state. It's critical because now adding just one more grain of sand might do almost nothing, maybe a tiny trickle of a few grains, or it might trigger a huge avalanche that reshapes the whole pile. And the key is, the system gets to this state by itself, without any external tuning. It self-organizes to criticality.
And once it's there, the sizes of the avalanches follow a power law. Lots of small ones, fewer medium ones, very few huge ones.
Precisely. Small inputs can have small or large outputs. The potential for the big event is inherent in the system's state, not necessarily in the size of the trigger. And this simple sandpile idea turns out to apply incredibly well to things like, well, mass extinctions in the fossil record, financial market volatility, even traffic jams.
Wow. So a 4-hour gridlock from just a few extra cars or a mass extinction from maybe a not-so-huge asteroid, it's the same principle. The system was already poised at the edge.
That's the SOC perspective, yes.
Yeah.
The system is primed.
Okay, let's bring this home. We've got sensitivity to initial conditions and feedback loops. Let's apply it to the biggest complex system around, Earth itself. This is where Jim Lovelock's Gaia hypothesis comes in.
Right, Gaia. Still controversial in some circles, but the core idea is powerful. Lovelock proposed that Earth's living organisms and its non-living components, atmosphere, oceans, rocks, interact as a single, vast, self-regulating system, a system that actively maintained conditions suitable for life.
Self-regulation on a planetary scale, how did he even start to argue for that? What was the evidence?
His Mars test was crucial. He looked at the atmospheres of Earth compared to our neighbors, Mars and Venus. Mars and Venus have atmospheres pretty close to chemical equilibrium. Mostly carbon dioxide, stable, not much happening chemically, which you'd expect on a dead planet.
Makes sense. Rock and gas chemistry left alone.
But Earth, our atmosphere, is way, way out of whack chemically. It's far from equilibrium. We've got loads of oxygen and methane coexisting. Chemically, they should react and destroy each other pretty quickly. The fact that they persist in such high concentrations is, for Lovelock, strong evidence of active biological regulation. Life is constantly pumping these gases out, managing the thermostat and chemistry through enormous feedback loops.
That regulation idea is captured in the Daisyworld model, isn't it? Simple but elegant.
It's a fantastic teaching tool. Imagine a planet with only two life forms, black daisies and white daisies. Black daisies absorb sunlight, warming their surroundings. White daisies reflect sunlight, cooling things down.
And they just act in their own self-interest. Black ones thrive when it's cool, white ones when it's hot.
Exactly. There's no conscious plan. But as the sun's brightness changes over time, like our sun has, if it gets hotter, white daisies do better, reflect more light, cooling the planet back down. If it gets cooler, black daisies gain an advantage, absorb more heat, warming things up. Through this simple feedback, temperature affects daisy populations affect temperature. The overall planet temperature stays remarkably stable within the optimal range for daisies.
A planetary thermostat built from selfish daisies. It demonstrates the power of feedback in maintaining stability within complexity.
It really does. And Lovelock argued that Earth's biosphere operates on similar, though vastly more complex feedback principles.
And zooming in even further, this deep simplicity seems to show up right down at the level of life's own structure.
Absolutely. Think about how life scales. Metabolic rate in mammals, for instance. How much energy we burn compared to our size. You might expect it to scale with volume, like a power 3, but it doesn't. It scales with a power closer to 2.25, or maybe 3.4, depending on how you measure. It's a power law.
Which hints that our internal plumbing lungs circulatory system isn't just filling space, it's structured like a fractal, maximizing surface area for exchange.
That's the interpretation, yes.
Yeah.
To efficiently transport oxygen and nutrients throughout a 3D body, life seems to have evolved these fractal-like distribution networks. It's maximizing exchange surface area within a finite volume, using the same kind of scale invariant power law math we see in earthquakes or river networks. The complexity of life seems built on these simple geometric and physical rules.
Okay, so let's wrap this up. We've journeyed from Newtonian certainty through the unpredictable cliffs of chaos, but found this surprising order of fractals, power laws hiding underneath, and stabilizing feedback loops like Gaia. What's the big takeaway for you, the listener, from this deep dive?
I think the core lesson is, well, it's actually quite liberating. Stop looking for incredibly complicated, unique reasons for every big dramatic event. A massive stock market crash, a huge extinction event, a giant landslide often. These aren't caused by some extraordinary rare trigger. They're more likely the extreme end of the normal behavior of a complex system operating near criticality, governed by simple rules and feedback. Understanding that lets you focus on the underlying system dynamics, not just the latest big headline event.
So appreciating the deep simplicity beneath the surface complexity.
Exactly.
All right, we started with Lovelock's two simple ideas, sensitivity and feedback. Let's end with maybe the ultimate application of thinking this way, the search for extraterrestrial life.
Yeah, this is where it gets really exciting. The whole strategy for finding life elsewhere is now deeply informed by complexity science. If life exists on another planet, it's likely to be a complex, self-regulating system. Just like on Earth, it will probably push its environment far from simple chemical equilibrium.
Creating a planetary scale signature of life, a global feedback loop in action.
Precisely. So we don't necessarily need to send a probe to find a single alien microbe, though that would be amazing. Instead, telescopes like the James Webb Space Telescope are designed to analyze the light filtering through the atmospheres of exoplanets, planets orbiting other stars.
Looking for that chemical imbalance, the atmospheric fingerprint of active biological regulation.
That's the dream. If we detect an atmosphere that's wildly out of chemical equilibrium, maybe lots of oxygen and methane together, like Earth, that could be incredibly strong evidence for life. Finding that planetary scale signature of complexity and feedback, that might be how we first discover we're not alone, using those two simple rules to answer one of the biggest questions humanity has ever asked.